Hey folks, in this video we're talking about hydrates and formulas of hydrates. Wow, 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 wow. I would like you to be able to describe what hydrates are and why they matter. And I would like you to be able to determine the formulas for hydrates from experimental data. So let's talk about that. Hydrates are compounds that can combine reversibly or reversibly combine with water. So there's different types, but we're going to deal primarily with hydrates of ionic compounds. But just so you know, all these hydrates are really dope. And so an example would be cobalt chloride. So if I take cobalt chloride and I combine it with, for instance, 6 waters, they can combine together. And we represent that with this little dot that says that these 6 water molecules are part of this cobalt chloride complex. They're all complex and complexed together. Formulas for hydrates are, as shown up here, we're going to have our number of water molecules combined with a combined separated by a dot. That's not that confusing. Oh wait, yeah it is. But either way, we're going to show the number of water molecules that have combined separated by a little dot. Yes. And so here we have an example of cobalt chloride with 5 waters attached, magnesium chloride with 4 waters attached. Now the name of the compound is going to be the same, except we're going to add a little bit on to indicate that it's a hydrate. So this is going to be Greek prefix hydrate on the end. So we remember our Greek prefixes hopefully from our time dealing with covalent compounds. So for instance, our cobalt chloride with 6 waters would be cobalt chloride hexahydrate. Hexa for the 6 waters. If we were looking at this copper chloride, the proper name for this would be copper 2 chloride pentahydrate because there are 5 waters. And this dude, what do you think this dude's name would be? Pause the video and think about it. Well, that's right. It's going to just be magnesium chloride tetrahydrate because there are 4 waters attached to it. Very cool stuff. What are hydrates used for? Well, actually pretty important stuff. We use them for dehydrating things. So if we have one of these dudes that is not in the hydrate mode, it will suck water out of the air in order to form a hydrate. So if you want to dehydrate something or suck the water out of it, you can use a salt and turn that salt into a hydrate. They're also really good for keeping things dry. Like if you've ever bought a new pair of shoes and found a little packet of like stuff that says "don't eat" in there, that is a desiccant, and that is going to form a hydrate. It's going to pull water out of the air to make sure that your shoes don't get wet while they're like not your shoes yet and waiting to be sold, because if they got moldy, that would be bad, and then you wouldn't want them. Anyway, let's keep going. So if we want to determine the formula for hydrate from experimental data, pretty easy process for that. First thing that we're going to do is we're going to get the mass of the ion hydrate. We want to know, we're going to start with some ion hydrate, and we want to know what mass we have. Then we're going to heat that sucker, and that's going to kick out that water. Just like if you took a pot of water and heated up and boiled it, the water would go away. It would become a gas. Same thing's going to happen with a hydrate. If I take some hydrate and I heat that sucker up, the water molecules are going to leave as a gas. And so now I'm going to get a new mass. I'm going to take the mass of that hydrate salt, or that dehydrated salt, which will be a pure ionic compound at this point. No more water attached to it. And so I can find the mass of my pure, the difference between this new mass of the dehydrated salt and the ion hydrate is going to be the mass of water. So the change in mass will be all water. Okay, so then I'm going to convert these masses into moles. I'm going to divide my moles of water by the moles of ionic compound to get the ratio between them. So let's look at an example. I know I've got a mass of an unknown hydrate. I have a mass of the pure ion, and yep, that's all I'm given for starters. Why don't you just, based on these steps, pause the video and see if you can tackle this dude. Okay, cool. Well, you try tackling that on your own. Let's talk through it together. I know the difference between my starting mass of the ionic dude and my ending mass is going to be the mass of water, right? Because in this formula, we've got water. In this one, we don't. So the mass of water has got to be the difference. So I'll subtract those two values to get my difference of 6.11 grams. I know that that's how much water was in this compound. Okay, now I'm going to convert my masses into moles. I'm not going to mess around with this dude because I don't know the formula, but I can change my calcium chloride into moles using the molar mass. And I can also do the same thing to water using that molar mass. Okay, so now I'm going to divide my moles of water by my moles of ionic compound and get a ratio. That's going to be 3 when I do that moles of water divided by moles of CaCl2. And this tells me the ratio between my pure ionic compound and water. This tells me my formula is CaCl2.3H2O. There are 3 molecules of water for every 1 molecule of CaCl2. Neat. And so this guy would be calcium chloride trihydrate. Let's look at another example because that was so dope. Why don't you pause the video? This dude is way more spicy, but why don't you pause the video and see if you can handle this dude on your own? Cool. Well, let's talk through it together. In this one, we're actually told about a crucible. Usually when we are making hydrates, we will have a crucible or a vessel from the lab that is supposed to get heated. And we're going to put our hydrate into the crucible, heat that sucker up, and then we're going to weigh at the end the crucible and the pure salt that's inside it. We'll generally weigh those together because it's annoying to try and get that salt out of the crucible. And we might not get all of it. I don't know why I'm adjusting my screen. Anyway, pause the video, try this problem out. Cool, let's do this. So we know here our mass of the hydrate, and that's all we really know for certain at this point. But we can calculate our mass of the pure salt because we know the mass of the crucible, and we know the mass of the crucible and the salt together. So we'll do the mass of the crucible and salt minus just the mass of the crucible. So that's going to be 28.35 grams minus that 21.41 grams for that crucible. That tells me that the pure salt weighs 6.94 grams. And now I can find the difference between my hydrate and pure salt. That's going to be the mass of water. So I'll do the mass of the hydrate minus the mass of the salt, and that's going to give me 4.84 grams. All right, let's keep going. I'm going to convert these dudes both into moles using their molar masses. Hot sauce. And now I'm going to divide my divide my moles of water by my moles of that salt, and that's going to give me 6. This is the ratio between the water and salt. This tells me there are 6 water molecules for every one of the salt. And this dude will be named nickel 2-sulfate hexahydrate. Very, very nice. Very, very nice. Well, that's the end of this video. I hope you understand what hydrates are in chemistry. I hope you understand a little bit about how they're used and why they might be important. And I hope that you can calculate the formula for a hydrate if you have experimental data. Cool. Ta-ta. Have a great rest of your life.